after looking into this FCFS, SJF and the shortest remaining time first algorithms, so next algorithm that we have in the scheduling policy that you can find in most of the computer systems is the round robin policy. So, as the name suggests, so there are a number of processes that we have in the system, and each process is given some small unit of CPU time. So, this is known as the time quantum or this Q. So, this is given for a small time quantum, and so this quantum value may be very small. So, that is we will come to those value related issues later, but suppose this time quantum value is equal to say 2 millisecond. So, what happens is that a job is given 2 millisecond for execution. So, as soon as a job is put into the CPU, so from the ready queue it is taken and it goes to the running state. So, simultaneously we start a timer. So, this timer when it expires, so this timer is for 2 millisecond, and when this timer expires, so at the expiry of this timer the scheduler is invoked again. The scheduler is invoked. So, what the scheduler does is that it takes the job out of the CPU and it from the ready queue it picks up the next job and puts it into the CPU. So, that is how this whole thing operates. So, if there are n processes in the ready queue and the time quantum is q, then each process gets 1 by n of CPU time in chunks of at most q units at once. So, 1 by n of the CPU time, so that is given to every process, and once a process gets the time, so it is for q time units, and it can be shown that no process waits more than n minus 1 into q time units, because if a job has to come, if a job has arrived, so and there are n processes in the system, then what can happen is that this is the nth process. So, before this fellow gets a chance for execution, so before this there are n minus 1 jobs, there are n minus 1 jobs before this. So, each of them will get a q time units, after that only this fellow will get a chance for execution. So, the wait time for this nth job is equal to n minus 1 into q. So, after that it will get a chance for execution. Now, whether it will complete in the q time unit that it has got, so that is a question, but the first time the response time that we have, so response time can be less, because you can predict what is the response time. So, in the previous algorithms, the FCFS, SJF etc., predicting response time was not possible, because it depends on the CPU burst sizes of other jobs, but here whatever be the CPU burst size of the previous jobs, so they all the previous jobs, so they are given only q time units. So, total n minus 1 jobs at most, so that is n minus 1 into q, that is the total time. So, this bound of n minus 1 into q, so this is a bound on the response time. So, it is so this response time is bounded by n minus 1 into q. So, timer quantum timer interrupts every quantum to schedule next process. As I was telling here, that as soon as a job is put into the CPU, the timer starts, and the timer when it expires, then it the scheduler is invoked, and scheduler takes out the running process, puts it back into the ready queue, and it is the CPU is given to the next process. Now, this time quantum for which the process gets the CPU, it is not mandatory that the process will use its entire time quantum. So, it may so happen that the process is a highly IO bound job. So, though it is given 2 millisecond, after executing for 1 millisecond it finds that I need to do some IO operation. So, it just comes out of the CPU. So, that case also scheduler is invoked. So, before the timer expires, the job gives control back to the scheduler. So, that way also it may be possible that the scheduler is invoked, and then again the next job gets the chance to execute. So, whenever a job is selected by the scheduler, the timer is started for 2 millisecond, and that way it continues. So, performance, if q is a very large value, so if the time quantum is very large, then what happens is that once a process gets the CPU, until and unless it voluntarily releases it, so it will be taken back only after q time unit. Now, suppose in a system we have got jobs of these processes, we have got 3 processes P1, P2 and P3, and their CPU burst sizes are 5, 6 and say 8. Now, if this q is equal to say 10, then what happens is that these jobs P1, P2, P3, so they will never face this timer going out. So, they will always whenever it is getting the CPU for 10 time unit, P1 will use for 5 time unit and then it will release it. P2 will get it, P2 will execute for 6 time unit and release it. So, that way this timer interrupt will never come into picture. So, the situation is exactly same as what you have in the FIFO policy. So, first in first out policy, assuming that P1 came to the system first followed by P2 and P3, the behavior will be exactly same as what you have here. So, the large this thing. Now, if q is made very small, okay, so instead of making it say 10 milliseconds, so if I make say q equal to say 1 microsecond, which is very small, then what happens is that the job gets the chance for execution, it executes for 1 microsecond and then the scheduler has to be invoked again to select the next job. So, in this part the scheduler is running, again the next job is selected, so that runs for 1 microsecond and then again the scheduler will come into picture. So, whenever this scheduler comes into picture, there is a context switch because the currently running process is taken out and the next process is started. So, you have to copy the context from PCB and all. So, that is a big thing. So, this context switching time becomes very high. So, q must be large with respect to context switch, otherwise the overhead is too high. So, if the context switching time itself is around say 2 microsecond, then if you keep this q to be 1 microsecond, then you see for every microsecond execution of job, you are wasting 2 microsecond in the context switch. So, that way the CPU utilization will be this throughput and throughput will be very low, CPU utilization is also low as far as jobs are concerned, and then your waiting time will be very high. So, this way the behavior will become very poor for the system. So, at both ends, making q very large or making q very small. So, both of them have got negative impact on the system performance. So, it is an issue to find out what is a good q value for a system. So, and again that is system dependent. So, there cannot be any general prediction like what should be the value of q. So, we can start with some value, and after that what we can do, we can look into the system behavior, and if we find that the system throughput is low or our waiting time is high, then we try to increase this q value a bit and see the effect. So, let us consider an example of this round robin policy with time quantum equal to 4. So, we have got 3 processes P1, P2 and P3, and their time quantum values are 24, burst time values are 3, 24, 3 and 3. Now, if we take the time quantum equal to 4, then P1 executes for 4 time units, and since its burst time was 24, so the timer expired at this point. So, P1 utilized full 4 time units and then the timer expired, and now P1 is taken out of CPU and P2 gets a chance for execution. But P2's burst time is 3, so after 3 time unit P2 finishes. So, now we have got P3, now it is P3's turn for execution. So, P3 executes for 3 time units and after that P3 finishes. Now, after that there is only one process in the system now, P1. So, P1 gets successive time quantums, the 10 to 14, 14 to 18, 18 to 22 like that. So, it finishes, entire thing finishes in 30 time unit. So, what is the average waiting time? So, average waiting time if you calculate, so then for P1 the total waiting time is equal to the time it is waiting in the ready queue. So, for P1 the waiting time is equal to 3 plus 3, 6 time unit. For P2 the waiting time is equal to 4, and for P3 waiting time equal to 7. Of course, in this particular case we do not find much difference, it is 10 plus 7, 17. So, it is like that FCFS policy only, but so if there are more processes such that so this P1 is not executing in successive time slots. So, in between some other processes are also coming. So, here in this region, then P1's time will be, P1's waiting time will increase further. So, in general, so average waiting time of this round robin policy is larger than others, typically higher average turnaround than SJF, but better response time. So, average turnaround time compared to shortest job first, yeah, it will be more, because it has to all the jobs are getting catered to. So, it is not given to a single job that way, unlike SJF where the shortest job gets the immediate attention to its completion. So, here that thing does not happen. So, every job is getting attention for some time equal to the time quantum. So, and that in a round robin fashion the CPU is given to the jobs. However, the response is better, the response time is better, because the job does not have to wait. Even if there, we have seen previously that if there are n jobs in the system, then the response time is at most equal to n minus 1 into q. So, that way it is good. Q should be large compared to context switching time. So, compared to context switching time, so Q should be large, so that we do not have the impact of this context switching time much. Otherwise, there will be large number of context switching if Q value is small, and each of those context switch, so that will take that context switching time. So, that way it will be a problem. Q is usually 10 millisecond to 100 millisecond for context switching time less than 10 microsecond. So, this is the range of values that we in different systems you can find out. Of course, there is no hard and fast rule, like it depends on the system that you have in your hand. So, normally it is a tunable parameter. So, context switching time is less than 10 microsecond, and this Q value, the time quantum value, is between 10 and 100 milliseconds. So, round robin is good, because this is for an interactive system. So, it is catering to all the processes. So, that way it is good. Now, this is a study on the quantum size. So, the performance of the round robin algorithm depends on the size of the time quantum. If the algorithm, the time quantum is extremely small, say 1 millisecond, then it can create a large number of context switches. Like here, so process time is say 10 and the time quantum size is 12 unit. Then it is the processor, the CPU is given to the process for 12 time units, it finishes in 10 units. So, there are no context switches, so context switch is 0. However, if the time quantum value is equal to 6, then after 6 time unit there will be a context switch, and then the process finishes at time 10. So, that way even if there is a single process, then after 6 time unit the timer will expire and the scheduler will come into picture. Scheduler will find that there is no other process to execute. So, it will continue with time 10, but for the execution of the scheduler itself there will be a context switch. So, as a result, this context switching, there is one context switching that will occur. On the other hand, if we have got a time quantum size of 1, so even if you have got a single process in the system, so every 1 time unit the timer will expire and it will send an interrupt to the system, and as a result the scheduler will be invoked and this context switching will happen. Okay. So, this between the scheduler and the process. So, there are 9 such context switches that are occurring in this. So, you see that if you make this time quantum very small, then the number of context switches will be very high, and as a result a good amount of time will be wasted in setting this in executing the context switches. Now, how does this time quantum size turnaround time varies with the time quantum? So, this is a graph of an example. So, suppose I have got 4 processes P1, P2, P3, P1, P2, P3 and P4, and their burst times are 6, 3, 1 and 7. And if you keep this time quantum value equal to 1, then the average turnaround time, so if you, so it can be found out. So, if it is 1, then what will happen is that, so you can calculate it like this. So, first P1 will be executing for 1 time unit. So, for 1 time unit P1 will execute. So, it is for So, for 1 time unit P1 will execute, then after that P2 will execute for 1 time unit, then P3 will execute for 1 time unit. Okay. So, then so P3 will be over at this time, then after that P4 will come for 1 time unit. So, in this way, so this now P1 will execute for 1 more time. So, this way you can draw a Gantt chart, and after that you can see that what is the response time, average response time for the processes, and it can be shown that if the time quantum size is said to be equal to 1, then this is the average waiting time. So, this is 11.0, whereas if you take that this is equal to 2, then the average waiting time increases. So, it becomes 11.5, whereas taking it to 3, the average turnaround time, so that reduces. So, this is so this turnaround time it does not necessarily improve as the time quantum size increases. So, in general the average turnaround time can be improved if most of the processes finish their next CPU burst in a single time quantum. So, this is the thing that it says that it shows that as you are increasing the time quantum size. So, when you are going to this value of 6 for example, then you see that most of the processes they can finish within one time quantum, and then the average waiting time starts to give good result. And if you set it to 7, then everybody can finish within one time quantum. So, that gives us the minimum average waiting time, but that is close to FCFS type of algorithm. So, that is so this response time will be a problem, but turnaround time will be reduced. So, but it is not mandatory, like when you are going from 6 to 5, this turnaround time increases significantly, and again going from 5 to 4, 5 to 3, turnaround time reduces, 5 to 4 also turnaround time reduces. So, there is no generic behavior of this graph. Only thing is that if it is beyond if it is close to the burst size of individual processes, then then the average waiting time will, average turnaround time will be minimized. So, this way it gives us some guideline about how to select this time quantum size. But another type of scheduling algorithm that we will look next is known as the priority scheduling. So, priority is a very important issue, because all the processes that we have in a system, so they need not have the same priority. For example, if we have got a system where there are signals coming from sensors like say smoke detector and all. So, so if there is a fire that comes up, then that has to be attended immediately. So, that way that has got a larger priority. Or consider a telephone exchange. Now, all the calls that are going through the exchange, so they are not of same priority. So, calls which are of higher priority, maybe the calls for which the tariffs are higher. So, for them the priority should also be higher. So, they should not face much blocking. So, for doing that we need to schedule the corresponding processes earlier than the processes which are of lower priority. So, normally in any process, in any operating system, whenever we create a process, we associate some priority with that. So, priority is generally represented by means of some integer number, and the CPU is allocated to the process with the highest priority. So, as a convention we can say that the smallest integer value will correspond to the highest priority, but it is just a convention. So, it may be the reverse also. So, the smallest integer has got highest priority. Now, the process when the scheduler is scanning the ready queue, then whichever process has got the highest priority, so that will be scheduled next. Now, this priority scheduling policy, so it can be both preemptive and non-preemptive. So, preemptive, non-preemptive means at the time of taking a scheduling decision, the scheduler looks into the priorities of the processes in the ready queue, and based on that whichever process has the highest priority, so it is getting the CPU. And once it gets the CPU, so it completes its execution, it completes its entire CPU burst, and after that only the scheduler is invoked again to see which process should be scheduled next based on priority. So, that is the non-preemptive type of priority scheduling. However, what can happen is that when a process is executing in the CPU, so there may be a new process that has arrived, and that newly arriving process, so it may have higher priority than the process which is running currently in the CPU. So, as a result we need to give this process priority. So, we need to preempt the CPU from the process which is currently running and give the CPU to the newly arrived process. So, that type of policy is known as the preemptive priority based policy. So, the CPU is allocated to the process with highest priority, and it can be a preemptive scheduling or it can be a non-preemptive scheduling. So, SJF is one type of priority scheduling where priority is the inverse of predicted next CPU burst. So, priority has to be computed. So, in SJF you can say that okay, we are as if we are calculating priority by calculating their predicted next CPU burst. And as we know that whichever process has got the least predicted CPU burst, so that gets chance for execution. So, here so that is the priority is the reverse inverse of this predicted next CPU burst. This priority scheduling problem, so it has got difficulties. One is called starvation, because low priority processes may never execute. So, as I have already said is like this, that if this ready queue that we have, so there I have got these processes. Now, this process they have got the priorities, maybe this process is of priority 5. So, this is of 2, this is of 1, this is of 10, this is of 9, like that. So, as far when the scheduler will be invoked next, so since this has the least this has got the least value. So, this is of highest priority. So, this is getting this process will get chance for execution. After that, this process with priority 2 will execute, then with 5, then with 9, then with 10, like that. But what can happen is that there may be a large number of incoming processes, there may be a continuous flow of higher priority processes that are coming to the system. As a result, the processes with priority values 9 or 10, so they may not get chance for execution at all. So, over a long period of time, maybe the process came to the system quite early, but due to the flow of these higher priority processes, so this process could not get a chance for execution. So, this is the starvation problem for this low priority processes. So, this is a very serious issue, because one process has been submitted, but it is not getting chance for execution because of these high priority processes are continually coming. So, this is the problem of starvation. So, one solution to the starvation problem is aging. So, what we do is that as time progresses, we increase the priority of the processes. So, every time so maybe I have got the ready queue. So, in the ready queue we have got these processes, okay. Then so all these processes have got different priorities. Now, what we do is that after some at some fixed intervals of time, we scan this ready list, ready queue, and we decrement all these priority values by 1. So, we decrement all these priority values by 1. Then what will happen? If a process is in the ready queue for a long time, so this process like with the priority say 10. So, next time this cycle is done, so this value will be reduced to 9. Next time this cycle will be done, so this will be reduced to 8. So, this way in successive cycles of this priority check, so this value will get reduced, and after some time, so this value will become so low that even if a new process that is coming to the system, they will not have that much low priority. So, maybe after some time, after 100 iterations of this loop, the value that we have here is say minus 90 for this priority for this process. So, no process will possibly join the system with a priority value lesser than minus 90. So, as a result, this process will be the highest priority process now, and next time the scheduler comes to select process from the ready queue, so this process is picked up for execution. So, this aging, so this is known as aging. So, as the process resides in the ready queue for a longer time, its priority is improved over the time. So, that is the aging process. So, as time progresses, increase the priority of the process. So, this solves the starvation problem definitely, and that is often followed in many CPU scheduling algorithms that uses this priority based scheduling. Now, this is an example of this priority based scheduling. So, we have got 5 processes P1, P2, P3, P4, P5, and their burst times are like this 10, 1, 2, 1, 5, and the priorities are 3, 1, 4, 5, 2. So, how these priorities were assigned? So, that is not an issue here. So, that the priorities have been assigned by some technique, okay, whatever be the strategy. They may be coming from different users, they may be due to aging and all. So, this is the current priority assignment. Now, since P2 has got the highest priority, so at time 0, P2 is scheduled. So, P2 executes for one time unit, then next priority is to P5. So, P5 is of priority 2. So, P5 gets a chance for execution, it executes for 5 time units, then next is P1. So, P1 executes for 10 time units, then it is P3, then P3 has got priority 4. So, it executes for 2 time units, and then P4 its priority is the last one. So, that it executes for 1 time unit. So, average waiting time in this case is you can compute for P2, the waiting time is, for P1 the waiting time is 6, for P2 the waiting time is 0, for P3 the waiting time is 16, for P4 the waiting time is 18, and for P5 the waiting time is 1. So, you can sum them up and then divide by number of processes. So, 16 plus 6 22 plus 18 40. So, that is 41. So, 41 divided by 5. So, that is 8.2. So, this 8.2 is the average waiting time. Now, this of course, so we cannot say anything in the sense that how this average waiting time will vary with priority, burst time, etc. So, that cannot be predicted because it is very much dependent on the job mix that we have. Okay. So, but this is a good policy because we can differentiate between the classes of processes that we have in a system. So, that way it is a good one. Now, you can club this priority scheduling with round robin. So, what we say is the system executes the highest priority process and processes with same priority will run using round robin. So, in the previous example that we had, so here all the priorities were different, they were distinct. Now, what if there are two processes with the same priority? For example, here if there are two processes that have both of them are having priority 3. So, there is another process say P6 whose priority is say, suppose we have got another process P6 whose priority is also 3. Now, between say P1 and P6 which one will be picked up? So, that is an issue. So, in this case it is said in the next policy that we are going to see, what will happen is that P1 and P6 they will be picked up in a round robin fashion, and that way both of them will have equal priority and they will execute in a round robin fashion. So, here we have got a situation where P1 and P5 they are having same priority, P2 and P3 they are also having same priority. So, first so if for P4 there is no confusion. So, P4 its priority is the highest. So, P4 executes for 7 time units, okay. Sorry, not this one. So, P4 has the highest priority. So, P4 executes for 7 time units. After that we have got P2. So, P2 and P3 both of them have got same priority 2. So, between P2 and P3, so there will be round robin. So, round robin size is the time quantum size is taken to be equal to 2. So, P2 executes for 2 time units, then P3 for 2 time units, then P2 again for 2 time units, P3 then 2 time units, then P2 so P2 has already executed 2 plus 2 4 time units. So, P2 will execute for 1 time unit now. So, that is there is 1 time unit P2 executes. After that P3, so P3 now is the only P3 is now the highest priority process and it has already executed for 4 time units. So, now it executes the remaining 4 time units. After that there is a tie of priority between P1 and P5. So, between P1 and P5 again we have got this round robin. So, P1 executes for 2 time units followed by P5 for 2 time units, then again P1 for 2 time units. So, P1 finishes at with 4 bursts. Now, P5's burst time was 3. So, it has executed for 2 time units here. So, it executes for 1 time unit more at this point. So, this way we can have this combination of this priority scheduling and round robin. So, they are taken together and then we get this type of scheduling. So, this is actually a compromise because it is difficult to maintain a large number of priority levels in a system. Like any operating system you look into, so there is a limit on the number of different priority levels that can be supported. So, many times so even if we want that the priority levels will be different, so it is not possible to create processes in all different priority levels. So, we group the processes together into some priority levels, so that it is suppose there are only 4 priority levels available in a system. So, if there are 100 jobs, so they will be distributed into these 4 priority levels only. So, within a priority level, so we follow round robin, and between the priority levels, so we have got this priority based scheduling. And in this particular example, you can find out that the average wait time is 8.2 millisecond, and that is the result of this. So, you can so depending upon the priorities and these burst time values, so this time will vary. So, that is the compromise between priority and round robin. Okay, so continue with this in the next class.